6.4 Day 1, the second part, has us stretching and compressing horizontally. So instead of affecting our outputs, this will affect our inputs today. Let's first define the period of a function. It's one complete cycle around the unit circle. And that's how we've defined our inputs for our parent function tables. So normally we start at 0 and we stop at 2 pi. Or we start at 0 and we stop at 360 if we were using that as our input values. In your equation, what will change that revolution around the circle is the b value that's right in front of your x term. So notice it's after the trig term but before the variable. And notice it's being multiplied to x, but what that does to that period of the function is it actually makes the period of the function change by division. And we can do the same thing with 360. So it'll either make your graph stretch or compress horizontally. To determine what your new input values are, we have to do a little bit of detective work on this. We'll first set bx equal to 0, and then we'll set it equal to 2 pi. And then what we'll do is we'll solve for x, and that will tell us our new start point and our new end point. All right, let's try a couple. Y equals cosine 1/2 x. Notice there isn't a number in front of cosine. That means our a value is 1. So we're not stretching or compressing vertically. But because b equals 1/2, that's going to do the opposite to all our x values. A value of 1/2, since that's less than 1, will actually stretch horizontally. If that was greater than 1, it would compress. It always does the opposite of what the coefficient says because it's your input value. To figure out what our table is going to look like, we're going to set bx equal to 0 and then 2 pi. If I set bx, which is 1/2 x, equal to 0, I would get x by itself simply multiplying both sides by 2. Doesn't do a whole lot for us. We're still starting at 0. But then watch this. If we set 1/2 x equal to 2 pi, and we multiply by 2 to get x by itself, we're going to end our cycle or our period of the function all the way at 4 pi. So that's going to affect our table pretty significantly. But as always, we're going to start with our parent function. Let's take a look at y equals cosine x, and we're just going to use our normal 5 table values and graph that function. So we have x and y, 0, pi over 2, oops, it's a pi there we go, pi, 3 pi over 2, and 2 pi. Now remember, cosine is your x value on the circle. At 0, cosine equals 1, then 0, then -1, then 0, and then back up to 1. Go ahead and sketch the cosine wave from the left side to the right side, noticing now that the graph goes all the way to 4 pi in both directions. Hopefully your graph looks something like this, and maybe even a little bit better than this. Sorry about that, you guys. All right, let's take a look at our new graph. So for our new table, what we want to make sure of is that we actually change the appropriate values. We're going to change our input values. So now for our new x, what we're going to do is instead of going from 0 to 2 pi, we have to go from 0 all the way to 4 pi. And I know I need 3 values in between. So halfway between 0 and 4 pi would be 2 pi. So I'm going to put that right in the middle. And then I'm going to split that up again. Between 0 and 2 pi, that's 1 pi. And between 2 pi and 4 pi, that would be 3 times pi. So those are now our new input values. And our outputs actually stay the same. 1, 0, -1, 0, 1. Remember, we said this is going to stretch horizontally. When we plot these 5 points, I'm still at 0, 1, but now I'm going all the way over to pi, then to 2 pi, 3 pi, and 4 pi. I'm going to do the same in the other direction, -pi, -2 pi, -3 pi, and -4 pi. If we connect these dots, notice we're still plotting kind of the same shape. Wow, my graph is so weird right now. Sorry, you guys. So we're plotting kind of the same shape, just stretching it along that x-axis. So we've stretched that curve horizontally. In this next example, we'll have vertical and horizontal changes. Notice there's a number in front of the trig term and a number in front of x. Let's just start with one at a time. In the example y equals 2 times sine pi over 2x, our a value is 2. And the number in front of the trig term always affects our output values. The amplitude is the absolute value of 2, so that's going to stretch vertically. And we know that will double all of the values in our table. B is pi over 2. And pi over 2 is approximately 1.6. So technically that's greater than 1. What that means is we're going to compress horizontally. So it's going to kind of squish in a little bit, which I know that's a super technical definition. To figure out how that works, we're going to make our table. Remember, we're going to set bx equal to 0 and to 2 pi. If we do that, we have pi over 2x equals 0. To get x by itself, we're going to multiply by 2 over pi, which seems kind of strange. But on that right-hand side, 0 times anything is just 0. At least today we're starting at the same point we normally do. When we set pi over 2x equal to 2 pi, and do the same thing, multiply by 2 over pi, those guys cancel. Now the pi's cancel on the right as well. And 2 times 2 is 4. So if you look at the graph that I gave you, notice it's not divided up with like pi over 2 and pi anymore. Now we're going to start at 0 and end at 4. What that means then is that we're going to have to figure out our divisions in between. As we think about graphing our parent function, y equals sine x, we're going to have to think about how we can put that on this coordinate system as well. So I've got x and y, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And our outputs are 0, 1, 0, -1, and 0. But pi over 2, pi, and so on isn't on our graph. We need to approximate. Pi over 2 is roughly 1.6. Pi is about 3.1. 3 pi over 2 is approximately 4.7, and 2 pi is roughly 6.3. Now let's plot those values on our coordinate system and see where we're at. See if it kind of looks like our curve from before. At 0, 0, and then at 1.6 up to 1, so around there. 3.1 just beyond that point, back to 0, or that value. 4.7, maybe down here a little bit. And then 6.3 back to 0. And we're going to have to keep going on this, so this is going to be a little tricky to approximate. Notice we're going a little bit more than 1.5 each time. So I'm going to roughly go to about that point on the right. And then if I go 1.5, maybe down here, or like -1.6, -3.1, -4.7. So if I connect my curve, just getting a rough idea of what sine looks like, and I'd probably go back down. That seems to be a fair shape for that curve. I think we're okay there. So now let's figure out what we're going to do with our new table. Okay, for our x's, we're not only going to change our x's, but we're also going to change our y's. For our x's, remember we start at 0 and we end at 4. And I need those divisions in between. Well, 0 and 4 is going to be pretty easy to work with. Halfway between 0 and 4 is 2. Oops, I missed a division here, didn't I? Wow, good work. Sorry, you guys. Let me see, where am I at here? Oh, all right, I'm just going to redo this whole thing. Sorry. Okay. All right, let's try our table one more time. For our x values, we know we start at 0 and end at 4. Okay, and then we need to figure out those values in between. So if we think about halfway between 0 and 4, that's 2. So I'll be right in the middle. Halfway between 0 and 2 is 1. Between 2 and 4 is 3. So today's the easy day to kind of figure out our new x values. Now notice our outputs. We said that a was 2. So we're going to multiply all of our outputs by that 2. We have 0, but 0 times 2 is 0. We have 1, 1 times 2, 0 times 2, negative 1 times 2, and then 0 times 2. Let's plot these points and see what happens to our graph. So 0, 0 is going to match up. At 1, we're at 2. At 2, we're at 0. And then down in negative 2, back up to 0. This is actually going to be really easy to complete this pattern. If we go in the other direction, from 0, we're going to go down to negative 2, back up to 0, like so. If we connect these points, now our graph is going to stretch vertically, so it's going to be taller, but it actually compresses horizontally, so it's kind of more squished in. It goes down and then up. Just kind of connect your dots with a curve if possible. Try your best. And there you go. So that's changing the graph by stretching vertically with your a value, and we actually compressed horizontally with our b value. All right, let's try one more together. Y equals negative 2 cosine pi over 3x. Thinking about what a and b equal, how will that change the shape of our graph? Notice right away a is negative 2. That's going to do a couple of things for us. The negative is going to reflect over the x-axis, and that's all the negative does. The fact that we take the absolute value of negative 2 for our amplitude, it's still greater than 1. It's going to stretch vertically. All of that just from the a value. B is pi over 3. And pi over 3 is slightly greater than 1. So this is just going to slightly compress horizontally. So it'll squish it in just a little bit. But not by much, because pi over 3 is just slightly bigger than 1. To figure out our start and end points, we set bx equal to 0 and equal to 2 pi. See if you can determine the start and end point. When you're done, press play and see if we got the same result. Did you come up with 0 and 6? I hope so. Now let's take a look at our parent function. Y equals cosine x. I hope by now you can write this out just super fast. You have these memorized. We have 0. Oh, hang on. We're going to do as our approximates, aren't we? Because we go from 0 to 6 for our new graph. So instead of 0 and pi over 2, well, 0 is fine. Pi over 2 is about 1.6, and then 3.1, 4.7, and about 6.3. So again, we're using our approximates because our table for our new function doesn't have pi in it. Our outputs for cosine are 1, 0, negative 1, 0, and 1. Go ahead and graph cosine, and then we'll move on to the new graph. Hopefully your graph looks something like this one. This would be the sine wave, and then, the cosine wave. There we are. That's great. Sorry, you guys. And then for our new graph, when we make our table for x, we need to go from 0 all the way to 6. So the only thing that's going to make us this a little bit different is I think we'll get some decimals here. Halfway between 0 and 6 is 3, so the middle is fine. But halfway between 0 and 3 is 1.5. And then halfway between 3 and 6 is 4.5. So that wasn't so bad. Remember, for our outputs, we take whatever a equals and we change our outputs by that exact same amount, and that will get the reflection and the stretch at the same time. 1 times negative 2 is negative 2. 0 times negative 2. Negative 1 times negative 2. Back to 0. And then back to 1. All right, this is our last graph. Let's plot these and see how it goes. 0 down to -2, 1.5, 0, 3 up to +2, 4.50, 6 back down to -2. Where's my 6? 5, so right there, sorry. And then we'd be at 7.5, back up to 0. So every 1.5, we move in the opposite direction. 3, back down here, like so. All right, so if I connect what I have so far, go down and then back up. So you'll notice I didn't do much for the stretching and compressing horizontally, but vertically we did have a stretch factor by 2. And it's upside down, so it reflected over the x-axis. And that's changing your graph both vertically and horizontally. Tomorrow, I'll check your notes and we'll do the last example together in class.